we're going to get started shortly. Let's give you a little list of first part today. Oh, that looks a little bit different than usual. We're going to be looking at section 15.9. That's the first thing we're going to be doing. And it's essentially how to change variables, how you do the change of variable technique in double integrals. So just like you might have heard, I'm sure you did, you've seen the technique in Calc 2, where you might have to integrate a guy that looks like this, and yeah, it ain't going to happen. So what we can do in mathematics is, if we don't like the question, then we can change it into something that we can get the answer to. We then get the answer to that question, and we use the solution to that new, easier problem to predict what the solution of the original one was. And essentially, substitution is the way that we go about that. So the u sub here would be x cubed plus 1. You differentiate with respect to x. You do the crossover. And then you divide everybody, in this case, by 3x squared to isolate the dx. So each of these pieces, all of them, are eventually going to be turned into things with u. So it's going to be an x squared over the square root of u, and the dx becomes 1 over 3x squared du. In this case, the x squareds cancel, and I have a guy that looks a bit like that. I then convert him into a more useful power of u. In this case, 1 over the square root is a negative half power. Then we integrate by adding 1 to the power, dividing by the new power. We then return the u back to the x's. And then we do some style points on it. And that is your pretty bog standard Calc 2 u sub question, right? Change a variable. And we're changing the variable from an integral that has x's to an integral that has u's. You all familiar with that technique? No surprises, I hope. In fact, you might have used it before, right? And when you had a variable separable, one of these pieces could quite easily have been a u sub, and I'm sure it was. Now, how do you extend that idea of changing the variable from a one-dimensional, x cubed dx situation to a double integral? And actually from a double to a treble and quadruple, but we'll focus on doubles. Well, it's a little bit more intricate than the typical u sub, and the reason for that is that there are two different transformations happening, right? We're not just doing like a u sub, we're actually going to be doing a two-variable substitution, typically called u and v at the same time. So the first thing that we're going to do is a skill building exercise. Just hide that. And it's going to be how to find what's called a Jacobian. The notation for a Jacobian looks like that. So if somebody says find that guy is a Jacobian, that's his name. Now you're going to be given your transformations like that, or at least you hope they're given them to you like that. So that's the first difference, right? Normally, wouldn't you be saying u equals x cubed or x squared plus 1 or whatever? But you notice here it's x is written down in terms of u and v, and y is written down in terms of u and v. That is still a transformation. Now, there is a formula for finding a Jacobian, and it looks like this. it involves matrices. And so we are going to find each of these four derivatives, and this is essentially a 2 by 2 matrix. And then these two vertical lines are what's called the discriminant of the matrix, or determinant, I should say. So that's going to be our plan. Let's take a step back and look at determinants of 2 by 2 matrices. Well, major, take away minor. If you remember Calc 3, we did that, for instance, when we wanted to find, the cross product. Remember the cross product? You did that. So in this case, it's 3 times 5. Take away, so the major diagonal is 3 times 5. Take away the minor diagonal, which in this case is that guy. So I get 15, add 3, and I get 18. So that's what finding the determinant of a 2 by 2 matrix is. It's major diagonal, take away minor diagonal. Okay, let's return back to this guy now. And, excuse me. Thought I'd caught that, but I hadn't. So it's remind you. It's that one we're doing. That other one I'll do. It's a different question. dx by du, dx by dv, dy by du, dy by dv. Now I've called it its right name. And in that question, x is going to be u squared plus v squared, and y is going to be 3uv. Okay, now we're good to go. Partial derivative of x with respect to u. Fix this, it seems a little bit out for some reason. No? Okay. Right, you differentiate u squared plus v squared. Let's see if I can get that. There, that's better. Well, you're going to get 2u. Differentiate with respect to v, you're going to get 2v. Differentiate this guy with respect to u, you're going to get 3v. Differentiate this guy with respect to v, and you're going to get 3u. Are you comfortable about these four partial derivatives generating these four terms? Any questions about that? Okay. Then major diagonal is those two guys. So 2u times 3v. Take away minor diagonal, which is those two guys. So take away, what's that? It's a u, by the way. Take away a 2v times a 3v. And it looks like I'm going to get 6u squared, take away 6v squared. And that guy is the Jacobian. So far, so good. Any questions? So, start you off. This is a version of question 1. In fact, there's 3 Jacobians, 2 by 2 at least. And in this one, the x is going to be 6u plus a v, and the y is going to be 9u take away v. I'm still not 100% happy with the angles that these are pointing at. Oh, God. Sorry about this, but I won't get this camera position right. I end up cutting things off. Okay, I think that's good. Right, this is what I'm seeing looks good. Is what you're seeing, everything should be to the left and a little bit of blackness to the right where typically pictures go and cover things up. Is that what you're seeing? Right, so we are good, thank you, Antonio. Right, for this guy, the Jacobian, which is this fella, it's partial derivative of x with respect to u, partial derivative of x with respect to y. Then you do y, I'm saying y, v. That guy with v. Okay, oh, they're going to be numbers. If you do this guy with respect to u, you get 6. And if you do it with respect to v, you get 1. With respect to u, you get 9. And with respect to v, you get -1. So the major diagonal, which is these two guys, goes first. 6 times -1. Take away the minor diagonal, which is what, just 9 times 1. And we get -6. We'll take away 9. The answer is -15. So our Jacobian, that guy, ends up being the number -15. Jacobians typically can be anything except 0. If you get a Jacobian and the answer is 0, then it's no use to you because it won't help you do any change in variable integral. Basically, it just means that the transformation isn't independent, that the first one is somehow or other connected to the second, which means you don't have two variables at all, you only have one. And it's kind of the laws of algebra says, if you've got two unknowns, you need two equations. You can't have one unknown and try and work with two equations, right? They don't work. So the bottom line is, if you ever get a 0, you're screwed up and go and try it again. Apart from that, your answer could be numbers, positive or negative. Your answer could be expressions using u and v, which is actually more likely. Let's try a version of 3. Oh, by the way, right now, I haven't told you any reason at all why you need to find this thing called the Jacobian. The reason why we need it comes from later on down here, where when you want to do a change in variable, you convert everybody from x and y into u and v, very similar to what you would do in Calc 2, but you add in this extra little guy, the Jacobian tu dv. It's a bit like a correction factor to the area. And so this is why we're doing it. It's part of the puzzle. It's part of what we need in the change in variable process. So that's why we're doing it. So in this one, we have x 7p e to the q. We have y equals 7q e to the p. Symmetric. And we're going to find the Jacobian. In this case, I'm doing p and q. So the derivative of x with respect to the first one, which is p, and the derivative of x with respect to the second one, which is q. The derivative of y with respect to p, and the derivative of y with respect to q. Right, if you differentiate this one with respect to p, you get 7e to the q. If you differentiate it with respect to q, you get 7p e to the q. Now move on to the y's. Differentiate this with respect to p, and you get 7q e to the p. And if you differentiate it with respect to q, you get 7e to the p. Now I'll do major diagonal. So it's that guy. times that guy. Take away those two guys. Well, 7 times 7 gets me 49, and e to the p times e to the q just gets me e to the p plus q. Take away 7 times 7 gets me 49, p times q gets me a pq, and that guy times that guy also gets me e to the p plus q. And for style points, I will pull out a common factor, and that leaves me with that guy. Are we comfortable with finding Jacobians? I'll take a thumbs up or a thumbs down. Got one thumbs up. The rest of you not voting. Up or down? We okay with these guys so far? That's it. Right, I got majority of you. Now, moving on. How about doing the same thing with 3 variables? So, how would we do a Jacobian of x, y, z being changed into a u, v, w? Well, you would just expand this idea, but it would expand into a 3 by 3. So you do an x with respect to the first, the second, and the third variables. You then do the y's, differentiate with respect to the first, the second, and the third variable. And lastly, you do the z's with respect to the first, the second, and the third variable. Now I need a question to go like this, so I'll do a version of question 4, where x is 7uv, y is 7vw, and z is, well, just because they want it to be, 3w. Yeah. Right. Differentiate this guy with respect to u, you get 7v. With respect to v, you get 7u. And with respect to w, you get big fat 0. Move on to this one. Differentiate y with respect to u, you get nothing. With respect to v, and then with respect to w. On to z. Differentiate it with respect to u, with respect to y, and then finally with respect to w. Now, if you've taken Math 250, then you know all about the derivative of 3 by 3, not derivative, the determinant or discriminant of a 3 by 3 matrix. If you've not done this, the closest you've came to this was when we did cross products and we called this guy I, this guy j, and this guy k. You remember that? This would be I, j, and k. This would be the 3 components of u. This would be the 3 components of v. Although you weren't told that, essentially what you're doing there was finding the determinant of that 3 by 3 matrix. So this is how it works. You take this guy, 7v, and what you leave behind is a little 2 by 2 matrix. So it's going to be 7w, 7v, 0, 3w. Check. First guy. Take away. You remember the I, take away the j plus k. Same process. Take away 7u. And when you take that one away, you're left with this 2 by 2 matrix, which is what? A 0, a 7v, a 3. One of these two is not right. Let me check it again. That's w. There, fixed in time. There. And lastly, this guy here goes 3u. Let's check the original. fix that. There, fix them. Now, the last one would be plus 0 times this, but since it's a 0, I won't write it down. I don't need it. We then go 7v. Remember, that's meant to say 3u. So it's going to be this guy times this guy, 7w times 3u, minus nothing. Take away 7u. Major diagonal is 0. Take away minor diagonal, 7v, 3w. And let's see what we get. We get a 7 times a 7 times a 3, so that's 349s. That's 350s, take away 3, so that's 147 UVWs. Take away that guy times that guy, 2 negatives make it a plus, so it's plus 49 times 3, which is 147 UVWs. So you get 294 UV. Try it again. 249 UVWs. Okay, 3 by 3 are downright ugly. I mean, right, there's a lot more work involved in them because you have to do it really in 2 stages. The first stage is to break down this guy into its 3 components. Each of its 3 components generates a little 2 by 2 that you have to get the answer to. Then you do them and combine the terms and hopefully something nice comes out. And that's pretty much those 2, because these are really just skill building. How to find Jacobians. So what I'm going to do next doesn't have any homework questions attached to it, although I wish it did, because I would have picked them. And the guys we're going to do is a thing I kind of promised you. So I recollect saying I was going to do it for you. Second one, here we go. Remember when we did polar, you had a dx and a dy, and it turned into an r, dr, d theta. And I just told you, trust me, you need that r because it's there. You remember that guy? And when we did spherical, we would do a dx, a dy, and a dz, and that would turn into a d rho, a d phi, a d theta. And there was a guy here. Can anybody remember what the guy that goes here is? Any takers?
Is that rho squared sine of e?
Okay, looks good. And in the same way, didn't I just say, look, I know it's magic, you need to have it, it needs to be there, right? And no particular reason why. Well, guess what? That guy is a Jacobian. That guy is a Jacobian. Do you see that the Jacobian allows you to transfer from x, y, z to 3 variables, or from x, y to 2 variables? And it's a kind of correction factor. Without that extra piece, the thing doesn't work. So let's do the easy one and let you have a shot at the ugly one yourself. So if I'm doing x equals r cos theta, and I'm doing y is r sin theta, then the Jacobian would be called that guy. And it will be the partial derivative of x with respect to r, and then with respect to theta, and the partial derivative of y with respect to r, and the guy with theta. Now, if you differentiate this guy here with respect to r, you get cosine theta. If you differentiate it with respect to theta, r cosine theta turns into negative r sine theta. Because when you differentiate a cosine, you get a negative sign. Now you move on to this guy. If you differentiate him, you get sine theta. And if you differentiate him with respect to theta, you get r cos theta. Now here is our major diagonal. And so that's going to get me cosine theta times an r cosine theta. Take away, and the minor diagonal is these two guys. And that's going to be take away a negative r sine theta times the sine theta. And that gets me r cos squared theta. Two negatives make a plus r sine squared theta. Pull out the common factor of r. And lo and behold, that guy is 1. Do you see where the r came from? It came from a change in variable. And the change in variable we used was polar. Now, there's only 3 change of variables that we know about that we deal with, and that is for 2-dimensional polar, and for 3-dimensional, isn't it cylindrical and spherical? And if you do cylindrical or spherical, you'll notice that there's an extra little bit that goes here, and that little bit is essentially the Jacobian. Am I convincing you that these Jacobians are important to know because they're part of the change in variable process? Are we good? Cool. Good luck with that one, by the way. If you feel brave and you want to try it, it's actually quite fun if you get it right. Okay, so basically what we have now is what, another six questions, 7 questions, where we're actually going to get integrals that in their original format are no good to us, right? They're just too hard to do. They just don't make sense, whatever you want to call it. The change in variable process is not clean. Like in Calc 2, I would call that clean, right? You pick a U sub, the integral turns into something reasonably nice, then you integrate it. This has a lot more work to it. And basically, I've broken it into 3 chunks. The first thing you're going to do is find the Jacobian of the change in variable. Then we're going to have to change the limits of integration. Normally in Calc 2, once you've got the answer in terms of u, you would convert it back into x's, and then you could put the limits of integration in. That really doesn't work with these. So what you have to do is you have to change the limits of integration that they give you into u is between 1 and u is between 1 and 4, and v is between u and v is u plus 1, right? You have to turn the limits of integration into things using u and v, and that's a new skill. And that's not always going to be very clean. And that's probably where you're going to have the biggest issue. And then lastly, once you've done all that, you can take the double integral that was horrible, convert it into this double integral. Now, when we look at it, I've got a little thing that's causing me thing there. Is there a little black band covering up that writing at the bottom? Because I can't always tell what you're saying. Is there one? Yes, no? It's covering up my bottom bit.
I don't see one.
Good. So it's just my issue. Right. Can you see this guy right at the bottom? The double integral of some region D of a function in terms of x and y is going to be converted into a double integral using new limits of integration, I'm calling them S, of the function where this guy is turned into u's and v's, followed by our Jacobian friend, that says x, y, u, v, by the way, du, dv. In fact, if you kind of look at the notation, can you see the uv cancelling out with each other? That x doesn't look even vaguely x-like there. How about that? Make that y look more like a y. Do you see the uv's cancel kind of this way? And that's essentially the algebra looking version of the formula. Okay, let's jump right into it. These questions are messy and you have to be careful. We are going to find the double integral over some region R of a very simple integral. And dA is just code for dx dy. And we are given the substitutions that we're going to use. Okay, so step one is pretty straightforward. We're going to find the Jacobian. So it's going to be the derivative of x with respect to u, the derivative of x with respect to v, the derivative of it, oops, there we go, the derivative of y with respect to u, the derivative of y with respect to v. Do it with u, you get 9. Do it with v, you get 1. Do it with u, you get 1. Do it with v, you get 9. And major diagonal, oh, they're all numbers, that makes life easy, is 9 times 9, which is 81. Minor diagonal is 1. So the Jacobian is 80. Now, here's a little idiosyncrasy. Do you notice that this Jacobian has an absolute value around it? What that means is that when you're doing a Jacobian, at least when the answer is a number, it doesn't really matter when it's a variable because that takes care of itself. But if it's a number, it must be positive. So the Jacobian must be positive if the answer is numerical. So if this had came out as negative 80, right, because it could have, then the absolute value guy would have converted it back into 80, right? So if it's a number, it must be positive. If it's an expression, you don't need to worry about that. The math will take care of it, essentially. So that's step one. Get the Jacobian is equal to A. Now it gets messier because in that question that I just gave you, this one up here, the region R is described as a triangle joining 0, 0 to 9, 1 to 1, 9. So in terms of X and Y, here is 0, 0. Let's call that guy 9, 1. And let's call this guy up here, let's call him 1, 9. Now, if you try to do that original integral, which is this guy here, I guess I should write him down, the original integral over this region R, if I try to do it, you know, the vertical one, right, scanning x's, can you see the problem's going to be 2 lines up to here and then 2 other lines? That's very messy. If I try horizontal, can you see it's 2 lines up to here and then the lines change? Or at least one of them changes. It is, I guess, possible to do it in terms of X and Y, but not very, well, practical. So this stage, find the limits of integration for this region in terms of U and V, basically is going to get us to try and figure out what each one of these guys here that make up this triangle, what they look like in terms of a new space, which I'm going to call the UV space. And this triangle is going to get transformed into the UV space. Now, it might get transformed into a rectangle. It might get transformed into a nicer triangle. Whatever it is, that's fine. So I'm going to take each side of this triangle, find what the equation of the line is in terms of X and Y, and then convert it using these guys into U's and V's. So here goes. I guess I'm going to have to call them things. How about line 1, line 2, and line 3? Okay, I'll start with line 1. Passes through the origin, passes through the point 9,1. If you do rise over run, would you agree that the slope of this thing is 1/9 x, and that's its equation? Are you comfortable with the straight line? That guy there, number 1 as I've called it, has the equation 1/9 x, right? Its slope is right 1 for every 9, and it passes through the origin. Now, what does that look like? Well, y becomes u plus 9v, and it's 1/9 of x, which is 9u plus v. So that's going to be u plus 9v equals u plus 1/9 v. So far, so good. Now, if you subtract a u from both sides, you get that. If you take 1/9 v from both sides, you get 80/9 v equals 0. So actually, you just get v equals 0. So line 1, oops, wrong direction. Damn it, too quick for my own good. V equals 0 is this guy here. So there's line 1, v equals 0. Let's take line 2. Line 2, actually, let's do line 3. See, it'll be easier. Line 3 is this guy, and line 3 is y equals 9x, passes through the origin, and its slope is 9. The y gets replaced by u plus 9v again. The 9x gets replaced by 9 lots of 9u plus v. Oh, cool. They cancel out. And guess what? U equals 0. So that guy that I did here is actually line 3, and it's u equals 0. Now there's a third line, which is line 2. I'll try and squeeze it in here. And I'm going to find the equation of it using x's. I'm then going to replace the x with this guy. I'm going to replace the y with this guy. And I'm strongly suspecting I'm going to get some kind of line going like that. And I want the line, I want you to think of u as the new x and v as the new y. So I want this third line, right, which is going to be line 2, to be written in the format v equals so many u plus a number, just like you would say y equals so many x plus a number. So that's my goal. Well, first things first, I need to find the equation of this line. And I definitely need to do it a little bit at the side. I'll call this guy x1, y1. I'll call this guy x2, y2. The slope is y2 take away x, that's the other guy. So what's that going to be? 1 take away 9 over 9 take away 1. That's -8 over 8. Oh, good, -1. And then I'll use the point slope equation. Y take away 9 is -1 x take away 1. Y take away 9 is -x add 1. Y is -x add 10. Okay. So we have y equals -x add 10. I'm going to replace the y with u plus 9v, and it's going to equal -x, which is this guy, plus 10. So I want V on the left-hand side, and I want it to be V equal when I'm finished, and then all the other stuff on the right. So what I'm going to do here is add a V to both sides, take away a U from both sides, divide everybody by 10, and there is my third line. And my third line would look like this. It's going to be line number 2, this line here, and its equation is V equals negative U plus 1. So we've taken this triangle in XY space, used these changing variables to convert it now into this triangle in view V space. And we should be set up now for the last piece of the puzzle. So the double integral over that region R, just basically this guy, of x take away 10y dx dv is now going to be this fella. And based on the way that this thing is set up, just like you would have done in the past, I think I do a black one. I'm going to do it this way. Oh, by the way, this guy's 0, and this guy's 1, and this guy's 1, right? If you needed to figure it out. So I'm going to go U from 0 to 1. Right? So that's U goes from 0 to 1. And V, well, on the bottom, you've got 0, and on the top, you've got U plus 1. So there's my limits of integration. V goes from 0 to negative U add 1. Right? That goes from 0 to 1. The X, well, it becomes 9U plus V. Take away 10Y, which becomes U plus 9V. Instead of a dx dy, we'll put in the Jacobian. And then we can do dv du. So it's going to be from 0 to 1, from 0 to negative u add 1, 9u plus v, take away 10u, take away 90v. The Jacobian, we found it a way back in the day. What on earth was the Jacobian? It was 80. And I'll pull out the 80 because it's just a pain. There we go. And what do I get? I got that guy and that guy is negative u, and that guy is negative 89v. Integrate that with respect to v, you get uv. Integrate that, you get 89v squared. Evaluated from v equals 0 to v equals u plus 1. Okay, plug in u plus 1 for v. So negative u plus 1. Take away 89 negative u plus 1 squared, minus a whole load of zeros, so I don't care about them, du. And that's going to be 80, the integral from 0 to 1 of u squared take away u, take away 89 u squared minus 2u's plus 1 du. And that guy, take away that guy, is negative 88 u squared. That guy, add that, so what's that, 160, 177. And when you're finished, and I'll take their word for it, you end up with negative 1200. That is a classic start to finish change in variable question. And it involved, as you can easily see, an awful lot of working in a lot of places where you could have, and I may have, gone wrong. But the good news is that all of them kind of look like that one. And once you've kind of perfected the process, then it actually is just a little bit more understandable. Okay. Now wait until I've done question 6 and then you can ask any questions, because sometimes you have to see it twice before you kind of see all the steps. So in question 6, we've been asked to do a double integral of 15x plus 15y dx dy. And the region R is a parallelogram. And that parallelogram is negative 2, 8, 2, negative 8, 3, negative 7, and negative 1, 9. And x is going to be 1/5 u plus v, and y is going to be 1/5 v minus 4u. Okay, that's all the information. Okay, let's start tackling each of the steps. Step 1 is going to be to find the Jacobian. So it's a derivative, essentially that guy. Partial derivative with u, and then with v, partial derivative of y with u, and then v. If you differentiate this guy with respect to u, you get 1/5, and with respect to v, you get 1/5. If you do this guy with respect to u, you will eventually get negative 4/5, and this guy you'll get 1/5. The major diagonal are those two guys, which is what, 1/25. Take away the guy that's there, well, it's take away negative 4/25. So you get 5/25, so you get 1/5. Since this is positive, I don't need to worry about changing it. So there's our guy. So I guess a little note to self that the Jacobian, when we need it, is that guy. Now the second part is going to be convert, right, find the limits of integration in terms of u and v of this guy here. So negative 2, 8 can be here. 2, negative 8 can be way down here. So I'm pretty sure looks like that. 3, negative 7 would be about here. Negative 1, 9 would be about here. And if I don't draw this accurate, can you pretend I did? Right. So yeah, it's a parallelogram, just like they said it would. This guy is made up of 4 lines. 1, 2, 3, and 4. Right? And we're going to find out what those 4 guys look like when you convert them into UV space. So that's right now XY space. So just like the last time, I am going to find the equation of all 4 lines in terms of X and Y first. And then I'm going to use X gets replaced by this and Y gets replaced by that and convert this into a new UV space. And this new shape should be nice. My gut feeling is it's going to be a rectangle. I hope it is. For no particular reason, I'm going to pick 1. So line 1 passes through the origin and its rise is 16 and its run is 4. So I know its slope is 16 over 4. I also know it's pointing down the way, so I know its slope is -4. And I know it's passing through the origin, so I now have the equation of -4x. That's our first line. Put a little note of the guys I'm going to use up here, so I don't have to keep going back and forward between the two. Okay, well, y is 1/3 v minus 4u minus 4 times x, which is 1/5 u plus v. That gets me 1/5 v minus minus what? Minus 4/5 u. And that gets me -4/5 u minus 4/5 v. Do you notice that these two cancel out? And I'm left with 1/5 v is equal to -4/5 v. If you add them to both sides, you get v equals 0. So I have got my first line. Line 1 is v equals 0, and v equals 0 is basically that line there. There's line 1. Anybody got a preference for which one of the 3 lines that are left I should do next?
Let's do 2.
So you like to do things in order, right? So 2 it is. In line 2, I have to find the equation of a line joining these 2 points together. Right. Now, since these are not easy, I guess I could count rise and run, and that would be part of the puzzle. Well, let's see if I can do that. But essentially, rise over run is this equation. So it's 9 take away 8 over -1 take away that guy. So it's 1 over 1. Its slope is 1. Oh, okay. And then y equals, y take away y1 equals m, x take away x1, and I'll make that guy x1, y1. So y take away 8 is 1 to x add 2. So y equals x add 2 add 8, x add 10. Right, so what does that look like? Well, if we convert the x's to 1/5 u plus v, and we convert the y's into 1/5 v minus 4u. And what I'm going to do for the next few lines is rearrange this until I get v equals so many u's plus a number, right? Which is what I suspect it's going to be. With a bit of luck, it might even be a number. So 1/5 v take away 4/5 u is equal to 1/5 u add 1/5 v. Oh, would you look at that? These cancel, and you end up with that I wasn't expecting, but I'm kind of happy. You just end up that u equals 0. Are you expecting that? That means line 2 is that guy. Hey, I think this thing is going to turn into some kind of rectangle. Correct? Looks like it might. Let's pick our third line, which is line 3. And I'm going to do a little bit of cheat here because I want to speed things up. Would you agree that line 3 is parallel to line 1, so its slope is -1? And I only need one of the points, so I'm going to pick this one because I want to call x1, y1. So the equation of this line can be done using the point slope equation. So it's going to be y odd 7 is -x odd 3. Y is -x take away 4. Okay. And the y is going to be replaced by this fella. And the x is going to be replaced by that guy. And so here we go. 1/5 v take away 4/5 u equals -1/5 u. Did I change anything there? I did. That's a minus. Okay, we're cool. Now I want one of those two to cancel out. So let's see. Check if I did my equation right. That slope is definitely -1. And that point is definitely 3 -7. Yep. So it's y take away -7, add 7, check. -1, x take away 3, that's good. Negative, that's good. That's good, okay. Trust the math. That times that. Take away 1/5 v, take away 4. Let's see. Now, okay guys, start looking. Where did I screw up? I want one of these two guys to kill each other off. What I would really like is those two to kill each other off. But it's not happening. So something somewhere is just not matching up. That needs to be a plus, and for some reason it ain't. Can anybody see the mistake? Because right now I can't. Anybody got it?
I think wouldn't the slope be -4?
The slope.
Well, because we
Because
got
what was that one? That one was 4, wasn't it?
it was -4, yeah.
Oh, thank you. There we go. Make that 4. -4x plus 12. -4x plus 12. Okay, let's pretend that we got the correct straight line. For some reason in my head, I thought that was -1, but actually it's not, isn't it? If you remember, the rise was a lot more than the run, and it was -4. So that should come out good. So 1/5 v take away 4u equals -4 times x, and x is -1/5 u plus v take away 4. So I have 1/5 v take away 4/5 u. That times that is 4/5 times u, and that guys where's x? Oh, here we go. That's a plus. So negative 4/5 here. That negative 4/5 times this guy is negative 4/5 v. Take away 4. There's the guy I was looking for. I think we have got kill. Add this to both sides, you get v equals negative 4. And so we did actually get a number after about the 4th attempt. And now I'm just going to, extend my guy down the way. And I'm going to do v equals negative 4. So that's still part of line 2. And v equals negative 4 is going to go here. And can I save some time? If I did the 4th side, will you trust me that the 4th side ends up being there, and that line there happens to the equation u equals 4. So our limits of integration basically is that box. And so the u's go from what, 0 to 4, and the v's go from, where do they go from? They go from negative 4 to, in this case, 0. And what we can do then is put all the pieces together, and we should be able to get our integral. So the original was this guy. And it's now going to be turned into u equals 0 to u equals 4. V equals negative 4, say to v equals 0. I'm assuming that I guessed that one right. 15x's turn into, I need to start writing smaller. 15x's turn into 15 of these guys. Plus 15y's turn into 15 of these guys. The Jacobian was a 5th. And then we can just do dv du. So let's see what we get here. By the way, if that's not 0, it's probably going to be 4. But I'm going for 0 because it looks nice and symmetric. That gets you 3u plus 3v. That gets you 3v. Does it? Yes, it does. Minus 12u. Still times a 5th. And a dv and a du. Three, and that gets me negative 9 with that 5th, so negative 9/5 of a u. 3 and 3 gets me 6, so 6/5 of a v, a dv, and a du. And at that point, I have had enough of this question. You can just integrate it in the usual way. That is heavy duty integration, whatever you want to call it, algebra to make the thing work. Moving on to, before we do that, with the exception of that one mistake, or that's 3 mistakes, whichever it was, are we comfortable with the process and the fact that you need to take very great care in all these little u's and v's floating about and slopes and lines? And if you do it correctly, at least things do come out nice. Are we good? Or any questions about the 2 that I just finished doing? Okay, I'll move on. This one actually looks nicer. And the guy, the region, is that guy. The good news is, do you know all that straight line stuff that we did with the other two questions? You do not need it for this one. By the way, if you wanted to know what this looks like, it's an ellipse. Now, no matter how you do an ellipse, if you try and do it horizontally or vertically, this is not going to come out pretty. It's not like a circle and we could do polar on it. However, they have told us that this is going to be the substitution to use. So all I'm going to do this time is take the equation of the surface, which is all the points inside that guy, right? And replace the x's with 5u's, and then square it. Replace the y's with 6v, and then square it. And what I'm now going to have is a different surface, but using u's and v's. So this is what x and y looks like. If you're really interested, 6 to -6 and 5 to 5, which is almost certainly where these guys came from. And 36 times 25. 36 times 25 gets me 900 u squared. 36 times 25 gets me 900 v squared equals 900. And if I divide everybody by 900, do you see that the new guy in UV space is a circle, radius 1? That'd be cool. That would be a circle. Now, isn't a circle much easier to do, right, than the original question? So what I'm going to do first, before we get too caught up on the details, is I'm going to find the Jacobian, because I need that. So the derivative with respect to u, the derivative with respect to v, the derivative with respect to u, the derivative with respect to v. If you do this guy with respect to u, you get 5. With respect to v, you get 0. This guy with respect to u, you get nothing. You get 6. Major diagonal is 30. There's our Jacobian. Since it's positive, it don't matter, right? So my integral right now is going to be over a new region, this region here, which I'm going to call S. So 6x squared dx dy is going to be a double integral over the region S. 6x gets replaced by 5u squared. The dx dy gets replaced by the Jacobian, and now it's going to be du dv. And so it's a double integral over the new region S of 25, oh yeah, that's big. Let's try it out. 25 times 6 times 30, which is 4,500. So I'm definitely putting that outside. 4,500 u squared du dv. Now, just when you think, okay, then I just need to find some limits of integration for u and v and Bob's uncle, but do you notice that that's a circle? And when it's a circle, isn't it easier to do polar than it is to leave it alone as x's and y's, or in this case, u's and v's? So I'm now going to do a polar on that guy. And the r value is 0 to 1. And it's an entire circle, so it's that guy. And so my region now becomes 4,500. The integral from r equals 0 to r equals 1, from theta equals 0 to theta equals 2 pi. I have u squared r dr d theta. And u, well, in polar, isn't u just like the x, so it's r cos theta. And v would be r sine theta. So technically, I guess I'm doing a second change in variable, but I'm kind of cutting corners because it's a polar one, we already know it. So can you see there's the Jacobian? All I need to do is turn that into r cos theta. And I'm doing that because u is the x's and v is like the y's. And now we have 4,500, the integral from 0 to 1, from 0 to 2 pi, and r squared cos squared theta times an r dr d theta. And this separates. So r equals 0 to 1 of r cubed times theta equals 0 to 2 pi of cos squared theta d theta. So we started off with an ellipse. We did a change in variable to get a circle. We used the fact that circles can be used in polar form, so we converted our question into polar form. Tidied it up by replacing the u squared by this guy, and now we have some variables separable. So it's going to be 4,500. This guy is 1/4 r cubed from r equals 0 to 1. And here's a little Calc 2 issue. How do you integrate cosine squared theta? What do you change cosine squared theta into so that you can actually integrate it?
1 plus cosine 2 theta over 2.
That works. So the integral from theta equals 0 to 2 pi. I'm just writing it slightly different, but yours is perfectly correct. It's that guy. Okay. I'm going to stop here, but this guy times this number times that number is 1125 pi. And I'll take their word for it because that's what they tell me in the answer grid. Of course, you have to distribute that and integrate, and 10 minutes later. I'm beginning to think these questions are at least 20, 25 minutes each. So it's good news that there's only a few of them, but that doesn't mean that it's going to be quick, because there is enough of them to take time. Oh, getting there. What's that? 8, 9, 10, and 11? Yes, okay. See if I can set one up. In question 8, we have a region, we have a 7xy, we have a dx, we have dy, nothing to see here. They describe the region R as bounded by y equals 1/3 x, y equals 2x, xy equals 1/3, and xy equals 2. And we are going to take this guy and these particular guys, and oh, I forgot to write down x is u over v and y equals v, right? That's transformation. And this is the region R, this is the transformation, this is the double integral. And I'm not going to draw these guys, since I already know what, I guess I would call it line 1, line 2, curve 3, curve 4, right? In no particular order, doesn't matter what order you do them in. And I will be able to convert these using these two fellas into a new region, which I'm going to be calling S. Well, let's get the Jacobian out of the way. keep doing that. Don't know why. I think I'm thinking of the next line. Okay. If you integrate this with respect to u, you get 1 over v. I should say differentiate. If you differentiate this with respect to v, you get negative u over v squared eventually. If you do this guy with respect to u, you get 0. And if you do it with respect to v, you get 1. So the bottom line is that the Jacobian is just 1 over v. So I know there's going to be a 1 over v. There's going to be a du dv going on. I know what 7xy is going to be. It's going to be 7 times u over v times v. And so my double integral over s, well, that u and that v are cancelling. So what do I get? It looks like, you check this out, 7u over v. That's 7u over v, okay? Okay, that's all right. So the only thing that's missing here is the limits of integration in terms of u and v. And as I said earlier, I'm not going to draw that guy. I'm just going to go algebra. So the first one says that. And this guy is v. And this guy is 1/3 u over v. Well, if I multiply both sides by 3 and then do that guy, I have a fella, which I kind of like. So I'm just going to leave it like that. The next one I'm going to do is y equals 2x. So that's going to be v equals 2 u over v. So what am I going to get here? V squared equals 2u. So how about that guy? Yeah, kind of like that. It's quite nice. I have xy equals 1/3. It's this one. So it's going to be uv times v equals 1/3. So that's u equals 1/3. I like that one. And then I have xy equals 2. U, that guy, equals 2. And that comes out to be u equals 2. And I like that. So I've got my limits of integration. U is going to go from 1/3 to 2. And v is going to go from, oh darn it, I do need some square roots. I like those guys, in fact. Yeah, okay. V squared is 1/3 u. V is a square root of 1/3 u. Yikes, I don't like that, but I need it. And v squared is 2u, so v is the square root of 2u. Oh, that is ugly. Okay. Square root of 2u, square root of 1/3 v, yeah. 1/3 u. There we go. You might have thought, well, why didn't I just, you know, have everybody in terms of u? The problem with that is, don't we need limits for u and limits for v? I can't change these because these are numbers. So that's a limit of u kind of fixed, which means I had to figure out what these guys looked like in terms of v. Yeah, we got them. Which means that we can now go to our integral, which we've pretty much taken care of. This guy here, and it's going to be the integral from u equals 1/3 to u equals 2. V equals the square root of 1/3 u to v equals the square root of 2u. And I'm assuming that 2u is bigger than 1/3 v. That's why I'm doing them in that order. 7 over u v times, well, I guess since it's set up this way, dv has to go before du. And I'll stop there. According to them, the answer is 245/36 log 6s. So be interesting to see how that comes out. Well, at least in this one, I didn't need to draw any pictures. I just used the equations that they gave me. And that's exactly what I'm going to do in question 9, but I'm only going to do half of 9 now. This is the original. The thing is set up as x minus 4y equals 0. This is what the region R is. It's a parallelogram made up of these lines. X take away 4y is 9. 5x take away y is 3. And finally, 5x take away y is 10. And what makes this question different from the others is there is no x equals or y equals. We have to choose our changing variable. And to make it a little bit different, I'm going to do it this way around. If I decide that u is equal to this guy and v is equal to this guy, can you see that the new limits of integration, the guy I'm going to call S, is simply just going to be u equals 0 to u equals 9, v equals 3 to v equals 10. So do you see, choosing your u and your v's is actually pretty straightforward. Right? Based on these guys, make these guys your u, and you get numbers, and these guys your v. Well, that's good, because I now have the limits of integration. I have u0, u9, v3, and v10. And that 5 I'm going to stick out here. X minus 4y is actually u. 5x minus y is v. The only thing that's missing is the Jacobian. And that's the problem, because don't we want this to be x equals a function of u and v and y equals a function of u and v, because we need them to be written in that order in order to get this Jacobian. So here's a little sneaky trick. The Jacobian that I want is this guy. He's 1 over this Jacobian. I know it's not a fraction, and I've said this when I do my Calc 2 students, but doesn't this notation behave similar algebraically to the way fractions behave? Basically reciprocal, isn't it? And so what I'm going to do now is find this guy. So the partial derivative of u with respect to x, the partial derivative of u with respect to y, the partial derivative of v with respect to x, and the partial derivative of v with respect to y. That's why so many times in the past I kept getting them mixed up, because there are 2 flavors to how to do this. Differentiate u with respect to x and then with y. Differentiate v with respect to x and then with y. Our major diagonal is that guy. Take away, our minor diagonal is that guy. So it's -1 plus 20. That is equal to 19. Since it's positive, I don't really care too much about changing its sign. So what's going to happen here is it's going to be 5. U equals 0 to u equals 9. V equals 0 to v equals 10. The Jacobian, oh, I almost made an error. the Jacobian that we are interested in is 1 over that guy, so it's actually 1/19. Right. This guy's 19, the guy you want is 1 over that guy, 1 over 19. So I'm going to have 1/19, which I'm going to stick out here, u over v dv du. And at that point, you should be able to finish it off. It's pretty nice. In fact, that one is variable separable, so it's even nicer. Are you comfortable with the little bit of magic which says that this Jacobian can be found by 1 over the reverse of the letters Jacobian? And it's a really nice property because it makes life, when you have a u sub in terms of x and y, it makes it nicer, right? Because it means you don't need to try and solve and rearrange this in terms of x equals a function of u and v, and the same for y. Any questions about that guy? Okay. Well, we're almost finished. We only have 2 left. Question 10 is pretty much the same as 9, so I'm going to only do about half of this guy. The double integral is this fella. It's 5x plus y e to the x squared take away y squared dx dy. And the region R is described by another, well, it's a parallelogram, but they call it a rectangle. That guy, that guy, that guy, and that guy. I mean, it could be a rectangle. It could be a rectangle like on its side. Okay. Now, based on what happened in the previous question, you have to pick your u sub, u and v. What are you going to make u and what are you going to make v? Any takers? And the clue is up here, of course. Take the obvious. You know, I'm getting close to retiring. I'd like to actually finish this class before we do that, so don't keep me hanging. If you're wrong,
X
you're wrong.
minus y and x plus y.
Right, go for the obvious. Yes. Now, that means u is 0 to 3, and that guy means v is u to 7. Do you see how simple the limits of integration are u and v when you choose this as your changing variable? So our integral is going to go u equals 0 to 3, v equals 0 to 7. I got a 5. X plus y is actually v, and this is a bit sneaky. But x squared minus y squared has to turn into u's and v's, or this isn't going to work. That guy has to turn into u's and v's. Any thoughts on that? Because it is actually sort of in front of us. If I write it like that, does that give you a clue? What is x squared minus y squared in terms of u and v?
UV.
U and v. Are we good? Now, the only thing that's missing here is that guy, right? once I get this guy in terms of u and v, we are good to go. And I'm going to use the same trick that we used for question 9. And basically it says, if you want to get this Jacobian, you can get it by finding 1 over that Jacobian. Let's see what that guy looks like then. Do it with x and do it with y. What's this guy? dv with x and dv with y. Okay, if you do this guy with respect to x, you get 1. With respect to y, you get -1. With respect to x, you get 1. And with respect to y, you get 1. So what do you get? 1, take away -1, you get 2. So the guy we're looking for is a half. So can you imagine that as a half? There's your guy. Because of that e to the uv, you will not be able to do a variable separable. But you might want to do it in this order. Let's stick that half so it's done. And the reason you might want to do it in that order rather than this one is that this one algebraically is easier to do, right? And if you do this one, you're going to have to do integration by parts. If you do this one, well, actually, you could probably do a u sub as well, but I would do an integration by parts. This way around, you don't need to. It's a lot easier. So that would be the version I would choose for this question. So we've kind of moved away from drawing the picture and creating the UV space, right, the new region S, to choosing our U and V substitutions based on the information that's given to us in the region R. So to finish this section, question 11. We're going to do a double integral over a region R of 5 times the cosine of y take away x over y plus x dx dy. And the region R is a trapezoid. Oh, it's a little bit different. And you join these 4 points together. And there is no u subs or x subs given. So this is like the ultimate version of minimal information, just enough to be able to do it, but not enough to make it easy. I need a u and a v. I am looking at this equation and I'm thinking to myself, this is my clue. So where do you think I might be going for my 2 substitutions?
Y minus x and y plus x.
Okay, that's where I'm going. Now, let's pull out the 5. It's going to be the cosine of what? U over v. I'm going to have to figure out who the Jacobian is. We haven't got around that issue yet. And du and dv. Now, these guys here are eventually going to give me my limits of integration, but we're going to have to work on that later, right? let's focus on just tidying up this piece here first. And then once I've figured out this guy, then we'll return back to figure out how to turn this shape into UV space. And that's not going to be easy. But this one is. That guy is 1 over that guy. And we can get this fella the usual way. If you differentiate this guy with respect to x, you get -1. With respect to y, you get 1. With respect to x, you get 1. With respect to y, you get 1. And at last, -1 times 1, take away 1 times 1. That answer is -2. Agreed? But we don't get negatives with Jacobians. That's why there's an absolute value around it. So our answer is in fact 2, which gets us a half. So that actually is the only time we needed to do that adjustment. Well, I now have 5. 2 limits of integration I don't know anything about yet. A cosine of u over v. Since the Jacobian's a half, I'll pull it out there. And now we're looking at du dv, right? So far, so good. Now, the last part is going to be the worst. Let's look at this trapezium. 2, 0 is here. 7, 0 is here. 0, 7 is up here. And 0, 2 is up here. Yeah, it is a trapezium, but it's actually worse than that. A normal trapezium would look like this, right? Do you see it's a trapezium on its side, and the fact it looks longer is just my scales. Okay. Now, each one of those 4 guys, and I'm going to call them line 1, line 2, line 3, and line 4. Each one of those lines has to be changed into what it would look like in the UV space. Now, in every question except this one, because this one is like the ugliest and the last one, we would already know what x was in terms of u and v and what y was in terms of u and v. But right now, we don't have that. Right? We just don't have that. Right? So we are going to have to work on, seeing what we can do. So I am going to have to take this fella and see if I can do some algebra on them. So u is y take away x, I'll call that equation 1, and v equals y plus x, and I'm going to call that equation 2. Now, if I add these 2 equations together, right, equation 1 add equation 2, I get u plus v equals 2y, and that tells me that y equals 1/2 of u plus v. So I now know what y is. It's 1/2 of u plus v. Now I want to get x. Well, how about putting y equals 1/2 u plus v into, I don't know, equation 2. So v equals y plus x, v equals y, which is this guy, plus x. V is 1/2 u plus 1/2 v at x. Take away 1/2 v from both sides, and take away 1/2 u from both sides, and now we have x. And I'll pull out the half as the common factor. And you get that guy. In fact, if I had used that, I could have got the Jacobian a half just by doing it the normal way around. So at least I've got that guy to work with. Okay, we have got 4 lines here. Give me a line. 1, 2, 3, or 4. Which one do you want me to figure out what it is?
Line 2.
Good, because I don't want the horizontal or vertical yet. This line here, right? I know it doesn't look it to scale, but if you look it from here to here, isn't it 7 by 7? So won't its slope be -1? And doesn't it pass through 7? So I can tell you its equation is that guy. Are we comfortable about equation 2 is y equals -1x plus 7? Are we good with that one? Okay. Then let's find out what it looks like in UV space. Y is -x add 7. Y is a half u plus v equals -a half of u minus v plus 7. So a half u plus a half v minus a half u plus a half v add 7. Those guys kill each other off. You end up with u equals 7. Ah, we have u equals 7, which is basically a horizontal line. A vertical line, I should say. Well, that was nice. Hey, let's go for 4, because I think 4 is going to be very similar, isn't it? Now, if you take this equation here, its slope is -1 and it passes through 2. So that's this guy. And so y is going to equal -x add 2, a half u plus a half v is -a half u plus a half v add 2, and you end up with u equals 2, which means another vertical line. So far, so good. So I actually do know some good stuff. I know that u goes from 2 to u goes to 7, and since they're numbers, they definitely belong there. I've got this fella. And I'm going to be doing the v first then, and the u second, because it makes more sense. What do you want next? 1 or 3? Line 1 or line 3?
Line 1.
Okay. Now, line 1 is a little bit tricky. Line 1 is essentially the line x equals 0, and it goes from y equals 2 to 7, right? So it goes from y equals 2 to y equals 7, right? So far, so good. Right, so what we need to do here is replace the y with, what shall I replace the y with? Okay, y is equal to 1/2 u plus v. Double everybody. Subtract a u from both sides. I got that. Well, don't really like that line. Looks good. Let's try x equals 0. Well, I know what x is, isn't it? It's a half u take away v. And if that's equal to 0, you get 1/2 u take away 1/2 v. And that guy is -1/2 v equals -1/2 u. Oh, I like this one much better. You get v equals u. The 2 to 7 doesn't matter. The 2 to 7 is going to be caused by these two guys. You see the 2 and the 7 here? I don't need to do those. Now, if I go the other one, which is what, line 3? And line 3 isn't y equals 0. And so y is a half that fella equals 0, which is basically that guy, which is that fella. Okay. And if I did the other one, I would just get a version of 2 and 7 because these two guys would end up being zeros and you'd get a 47. So I don't like that one. This I like. And so my region is going to be v equals u, which is basically a straight line going like this. And v equals negative u, which is another one going like that. So we have got that v goes from negative u to v equals positive u, and that's the integral set up. It's not a very pretty integral, but at least it's doable. And oh, you finished. How did that one go, guys?
There's a lot to juggle around.
Oh yeah, yeah. We are not talking baby stuff here, right? We are talking clever math, right? Lots of pieces. If you're thinking about the pieces, in my mind, the pieces kind of boil down to this. Find a Jacobian. Sometimes you might even have to do it the sneaky way, 1 over the guy, right? Find the limits of integration, right, which is all this work, and then put the package together. So even within these, there's a lot of little nuances, isn't there? Like your XY plane into your UV. It's much nicer when they just give you equations, you know. If I got an integral and they went and said it was made up of this guy, that guy, and that guy, wouldn't I already know who my u subs and my v subs are going to be? So in that world, aren't the limits of integration really easy? And hopefully the integral that you have would have something with these guys in it, you know? So that would be another verification that you were doing the right guy. That question, the ones that look like this, are a lot easier than this last one, where the amount of information you were given was really minute. They were just enough to get what you needed. So you had to take this guy, right? And you had to go there. The clue to my U sub was actually here, right? My U sub and my V sub. I think this is a kind of natural stopping point. So when I see you on Wednesday, we will be looking at a totally new section. We are going to be looking at vector spaces in 3D and then line integrals. So on Wednesday, we're going to be doing 2 new guys. It's going to be a lot easier on Wednesday compared to today. So I strongly suggest that you get started on these interesting questions as soon as you can, because you are going to, as you noticed, 20 minutes a question, it's going to add up. And you're going to have to fight your way through lots of little hiccups, some of which thankfully you caught for me. And I'm going to, your solutions to your midterm are now online. So we just hang about for a second, I'll show you, in case you're wondering where they are. Let's close that off and get some windows open that I do need. Okay, where the heck is my window? I need my window. Right. Come on, there we go. I'm just setting it up so it's student view. With a bit of luck, that should be easiest. and I should be able to share it. Here it is, I believe. Right, so are you looking at solutions to midterm exam with a number 2 at the end? Thumbs up, no, yes, maybe. Can you see it? Yeah, okay. Thank you, Antonio. Right, if I click on it, we'll show you what you get. Here is the original untouched question, and the highlighted guys are the solutions to the multiple choice. If any of those don't make sense to you, then you can, wait at the end of Wednesday, whatever day you want, and we can go over them. And here is the solutions to section 2 with the working that belongs with them. So hopefully you can look at your answers if you got them wrong at least and figure out why you got what you got wrong. Okay, bye-bye for now. I'll hang about because there might be some people with questions, and that's fine.